So today we're going to learn about compound events and Venn diagrams. Now remember, learning isn't always easy, so before we get started, let's take a deep breath, and then we'll get right into this. So compound events, Venn diagrams. I kind of want to start with this warm-up question, and we really don't need much knowledge of probability to tackle this. I want us to think, what's more likely to occur when you roll a fair six-sided die? Is it more likely that you'll get a number that's prime and an even number? Or is it more likely that you'll get something that's prime or an even number? And my hope is that you guys all sort of recognize that it's definitely going to be easier for us to get a number that's prime or even. And really that sort of comes from these English words and what we understand of them. The word and is effectively something that is restrictive, right? By using the word and, we need it to be both prime and even. I need to be both of two different qualifications, whereas the word or is effectively something that's inclusive, right? In this case, we get to include things that are prime or things that are even. I don't know that I really want to take the time to compute either of these probabilities right now. It wouldn't take a long time, but I really just want to sort of focus on this idea that when we have an and probability, we are restricting ourselves because we're needing to meet two qualifications, and when we have or, we're going to have a higher probability because we're including one or the other or both of them. Now, you may have seen in my previous video, I talk a lot about notation. Notation is really, really important for us as we build mathematical concepts. And so if we're going to discuss these probabilities more formally, we need some notation for it. So the first notation that we have is this one right here. Okay, it's read the intersection of A and B. Sometimes people would just say A and B, but formally it's the intersection of A and B. And it represents that both A and B occur. It roughly corresponds to the English word and. Okay, and then the second one, A with a weird looking U, B, we read that the union of A and B, and it represents that either A or B or both occur. So the union is that inclusive probability that we were talking about on the previous page, whereas the intersection is sort of the restrictive one. This union roughly corresponds to the English word or. Okay, now another thing I want you guys to know about is that these events, this A union B and the A intersect B, these are what are called compound events, okay? And they are themselves events, okay? In the same way that we could talk about the probability of A being, the same way that we can use this notation, P parentheses A being the probability that A occurs, we can now use the probability of A intersect B to mean the probability that both A and B occur. So this is this new notation. This one here is called the intersection, or you could think of it as A and B. This one over here is the union, and it's A or B. By the way that I keep track of these is that this symbol looks like a U to me, and so I think of that as being the union, whereas this one over here looks a little bit like an N, and so you can think about that as being intersection. It's hard because union also has an N in it, but just remember that the union one goes with the U-looking one, and the intersection goes with the other one. So now that we have this new notation, I want us to get an opportunity to practice that. So we're going to think about the same warm-up question that we were talking about before. We're now going to let the event A be that we get a prime number, and we're going to let the event B be that we get an even number when we're rolling a fair six-sided die. So in part A of this, I want us to express the probability of rolling a number that is prime and even using proper notation, and then find the probability. If you feel comfortable with that, go ahead and pause the video and try it on your own. If you're not sure, I'll go through it with you right away. So we want the probability of rolling a number that is prime and even. So it's the probability, prime and even. Well, prime was our A event, and even is our B event, and the problem said and, so this is going to be an intersection. Okay, so we would have the probability of A intersect B, and then it said find the probability. I think the easiest way for us to find the probability here is to use our sample space. If we think about our sample space being 1, 2, 3, 4, 5, 6, where are the numbers that are both prime and even? Well, the prime numbers are 2, 3, and 5, and the even numbers are 2, 4, and 6. So the only ones that are both prime and even is 2. So this would be a 1 out of 6 probability. Okay. So what we're practicing here is this idea that we can translate English into this mathematical notation and then figure out the probability that goes with that. So go ahead and try out B, and then we'll check that one, and then we'll go on to C. So the probability of rolling a number that is prime or not even. So this would be the probability of being prime or, now not even, we have a notation for that, right? Our notation is that we use the complement notation that we learned last time, this sort of prime. Okay, so that's the notation that we would use. Now, to figure out what the probability is, we're going to again go back to our sample space. We're going to think about this. Now, we want things that are prime or not even. So prime, that's these ones. And then not even would be this one, or this one, or this one. And then we then said or. To be or, I need to be either of those things. So that means I get to use 1, 2, 3, or the 5. Okay? So that looks like there are 4 things, 4 out of 6. So this would be a 2 out of 3 probability. Okay? So when we're looking at things that are or, it means that we're sort of putting together both groups of numbers. Okay? Now C, I indicated on here that it's a tricky one. Why is it challenging for us to express this idea, the probability of rolling a number that is not prime or even, using proper notation? And I'd encourage you to pause the video and think about that for a moment. So I hope you saw and understood that it's hard to tell here what the not applies to. Is this problem saying that the number is not prime, or it's an even number, or are they saying that it's not a prime number or an, like, it's sort of hard to tell if, and it's kind of like a parentheses thing. Do the parentheses go around the prime, or do they go around both of them? And I can't answer this one for you because it's hard to tell what this means in English. And that's going to sort of lead into the next thing that we need to talk about. And that next thing that we need to talk about is the idea that math notation should not be ambiguous. So it may be hard to go from English into math, but it shouldn't ever be hard to go from math into English. So we're not going to practice that going the other way around. I'm going to give you these expressions in math, and we're going to need to find a way to express those things in English. So I'm using the same events as before. A is again a prime number, B is going to be an even number, and we're working with a fair six-sided die. So the first one I have here is express the probability of A intersect not B in English, and then find that probability. So pause the video for a moment, try writing that out, and then we'll check in and see how you did. So hopefully you got that this is the probability of rolling a number that's prime, and also not even, so prime and odd. And so if I wanted to find that probability, I'm again going to go look at my sample space, 1, 2, 3, 4, 5, 6. I want numbers that are both prime and odd. So the prime numbers are 2, 3, and 5. The odd numbers are 1, 3, and 5. And the intersection of those, the and, is where both of them happen. So that means only 3 and 5. So this would be a 2 out of 6 probability, which we can reduce to 1/3. Let's go on to B. Again, I'd encourage you to pause the video, try and pick apart what that thing says, and then write it in English, and then we'll find that probability. Okay, so we should have read this as something like the probability of rolling a number that's not prime or not even. And in math, I mean, or both. It could meet both of those qualifications. To find the probability of this thing, I'm going to need to look at my sample space again. 1, 2, 3, 4, 5, and 6. So first we have the numbers that are not prime. So the not prime numbers are 1, 4, and 6. And then we have the not even numbers, so 1, 3, and 5. And if we want or, it means I'm including anything that meets either of those qualifications. So that means the 1 and the 3, 4, 5, 6. So basically everything except for 2. And so this probability is going to wind up being 5 out of 6 for us. I know that it can be sort of hard to figure out what these probabilities of things are, and so that's kind of why we're doing a lot of practice on these. Let's get into this last one. So as we've done before, pause the video, try it on your own. This one is challenging, but give it a shot. So the idea here is that we're working with a complement of a compound probability. So the compound probability is this idea of being A and B, so being prime and even. And then this is saying we want the probability of that not happening. So we will have the probability of getting a number that is not both prime and even. To find the probability of this thing, I'm going to go to my sample space again. And so I think what I want to do here is I want to focus on, let's look at A intersect B, and then let's just find the opposite of that, right? So first, finding a number that is prime and even, the only number that's prime and even is this one right here. And they said not to that. We want the complement of that, right? So the complement of this is basically everything else, which is sort of funny. It means it's actually exactly the same thing as B up above. So the probability for this is 5/6. So it's actually kind of a neat statement that we can write. We can actually say that the union of not A and not B is the exact same thing as the complement of the intersection of A and B. It's a lot of fancy math words all at once, but it's a true statement that we can write. So as you're probably finding, attempting to answer these questions by understanding their meaning in English is possible, but sometimes it's really challenging. Fortunately, we can use mathematical notation for more precise communication, and we can use diagrams to help us more easily find these probabilities. And so it turns out that Venn diagrams are really, really common in probability problems. There are a few different diagrams that we use, and Venn diagrams come up a lot. And we'll talk about how and when we use them later, but for now we're just going to learn about them. They're really, really important. They're a way to show your work on the IB exam and in your classwork. And so I want to start by sort of dissecting Venn diagrams and looking at what their parts are, right? So let's say that we have a Venn diagram, right? And I've got this Venn diagram, and over here I have the event A, and over here I have the event B. Okay, there are a lot of different regions in these diagrams, and I sort of want to take a moment for us to sort of look at where we would find certain locations in Venn diagrams. So for instance, if I asked you to shade on this diagram, where is the probability of A, right? Hopefully you recognize that the probability of A would be this entire A circle. Now, some of you might be thinking or wondering, wait a minute, like, should it be both of those parts? Some people might wonder, should the probability of A have been just this? Sort of like all of the A, but the A that doesn't include B. And the answer is no, but there is a special name for this other thing. This other thing would be the probability of A, and also restricting ourselves, forcing B to not happen. Okay, so if somebody wanted the full probability of A, you would respond with all of A. But if they wanted to say, yeah, I want A, but I only want the part of A where B doesn't happen, that person is basically saying that they want A and also for B to not be happening. Okay, so this is sort of how we can identify regions in these Venn diagrams. So I'd like to draw a couple more of these for you guys and sort of give you a chance to try out naming these regions. So what if I drew a Venn diagram and this time asked about this region inside here? How could I name that region? Like what would that be? Hopefully you recognize, like that region in there, that happens when both A and B happen. Well, we have a name for that. That's the intersection of A and B. Okay. What if I asked you guys to draw me a picture of the probability of the union of A or B? So to think about, what would it look like? How would I shade a diagram so that anything that's A or anything that was B was shaded? Well, hopefully you're recognizing that that would be sort of this entire thing here. That would be the probability of the union, A or B. And I know this video is running long, and I apologize for that. I've got two more of these that I'd like us to sort of look at, because this is a really, really valuable skill, and I don't want us to sort of skimp on our understanding of it. What if I asked you to shade the probability of not A and not B? You would sort of need to think, on this diagram, where do I find the intersection of not A and not B? Okay. one of the ways I like to think about this is I like to sort of think for a moment, like, where is not A? Well, not A is everything outside of A. Sorry for my terrible shading here. And not B is everything outside of B. Okay? Now, where's the intersection? Where did I shade doubly? Where did I double shade this diagram? And where I double shaded this diagram was on the outside of both of them. So this probability would be indicated by all of this stuff outside of here. We'll get some more opportunities to practice this as we get to our assignment for this, so I hope these made sense. If you need to, go back and look at them again. This idea of shading Venn diagrams based on notation is a really important skill. All right, so now that we've looked more closely at how to label these regions on Venn diagrams, it's worth noting that there's a really, really important formula that relates our and or probabilities that we can see really cleanly from the Venn diagram. And so imagine, if you will, this Venn diagram again. Here's A and here's B. If I wanted to find a formula for the intersection of A and, the union of A and B, A union B. Now think for a moment about what A union B is. A union B is A or B. So it's basically anything inside of this sort of, it's either a MasterCard symbol or it's like a fallen over snowman. So if I wanted to find that probability, what I could do is I could add together the probability of A, that would be this whole circle, plus the probability of B, that would be this whole circle. But if I added those two things together, doesn't that mean that I overcounted? Doesn't that mean that I counted this region right here twice? So in order for this equation to work out, I'm going to need to subtract off that region that I counted twice. But that region is the intersection. Okay, so this formula right here is a really important formula. We're going to use it a fair amount, although I'll be honest with you, lots of times I don't use the formula because I just draw the diagram. And I'm going to show you guys that in these next couple of examples that we do. I do want to point out, by the way, that the letters that I used in this don't matter. So for instance, if someone wanted to find the probability of A union not B, you could sort of use the formula the same way. It would just be the probability of A plus the probability of not B minus the probability of the intersection of A and the complement of B. So remember that it doesn't have to be used only with A and B. Whatever these two events are, you just put those events here and here and here and here. Okay? So now that we've sort of seen this in the Venn diagram, we figured out how to write these Venn diagrams, we're finally going to take this back and we're going to sort of figure out how to compute these compound probabilities. So I hope you're still with me and that these next few examples really clarify things for you. All right, so a cookie is randomly selected from a box. The probability of it having chocolate chips is 1/2, and the probability of it having nuts is 1/3. If a quarter of the cookies have both chips and nuts, what's the probability of randomly choosing a cookie that has chocolate chips or nuts or both? So what I want to do here is I want to take this problem that's written in English and I want to convert it to math, right? So first there's this idea of probability of having chocolate chips being 1/2, right? So the probability of chocolate is 1/2. Then we're told the probability of having nuts is 1/3. So the probability of nuts is 1/3. And then we're told if a quarter of the cookies have both chocolate chips and nuts, so that means the probability of chocolate and nuts is 1/4. And the question is asking, what's the probability of randomly choosing a cookie that has chocolate chip or nuts or both? So they're asking, what is the probability of chocolate or nuts? Okay. And so, we just learned a formula that'll do this for us, right? The probability of chocolate or nuts would be the probability of chocolate plus the probability of nuts minus the probability of the intersection of those two things. And I have all these numbers, I can just plug these things into the formula. This would be 1/2 plus 1/3 minus 1/4. And so if I get a common denominator on those things, this would be 6/12 plus 4/12 minus 3/12. Let's see here, that's 10, so 7/12. And that's our answer. Okay. I do want to point out, though, that for as much as this formula is nice, I really, really like being able to do these problems and not rely on just plugging numbers in. Like, formulas are great, but I worry sometimes that we don't think about what we're doing. And so I want to show you how you can do this on a Venn diagram as well, right? If you had a Venn diagram where this circle was chocolate and this circle was nuts, so we know that the probability of having chocolate chips is a half, so I'm going to write that as 6/12. By the way, the reason I'm writing that outside the circle is that it represents the entire circle. I'm worried that if I write it inside the circle, you'll think that it's just for the crescent part, and that's not really what I want here. We know that the probability of the chocolate chip having, not the chocolate chip, of the cookie having nuts was 1/3, so I'm going to write that as 4/12. And I know that the intersection of it having both of them is a quarter, which would be 3/12. So now here's kind of the magical part, right? If this whole circle has to add up to 6/12 and this part of it is 3/12, doesn't that mean we can automatically 12 what this part is? This part has to be 3/12. Similarly, if this whole circle has to be 4/12 and this section of it is 3/12, it means that this section over here has to be 1/12. And then when the problem was asking me, hey, what's the union, what's the whole, like what's all of these regions put together, we just have to add those regions up. It's 7/12. So the formula is great, but lots of times I don't really like dealing with the formula. I really just want to see it in the diagram so I can see these pieces coming together. When you do these problems on your own, you have a choice on whether you use the formula or whether you use the diagram or whether you use a hybrid of both of them. The thing I would encourage you is just make sure that you're showing your work. Now let's move on to the next example. All right, so I want to encourage you guys to try this one on your own. It's known that 80% of IB candidates take IB history and 70% take IB biology. If 90% of them take either history or biology or both, what is the probability that an IB candidate takes both IB history and IB biology? So again, pause the video, try this one out on your own. I'm again going to show it with both the formula version and the Venn diagram version, and we'll get the same answer either way. So let's see here. We know that, so I'm going to call the history event H and the biology event B, okay? So we're told that the probability of H is 0.8 and the probability of B is 0.7, and we know that the probability of the union is 0.9, and we're being asked for the probability of the intersection. Okay? So if we go to our formula, right? Our formula says that the union should be equal to one of the probabilities plus the other one minus the intersection that we don't know. Okay? And so now, this is just going to be a simple algebra thing. 0.9 equals 1.5 minus the probability of the intersection. If I move this thing over, I'm going to wind up with negative 0.6 is the negative probability of the intersection, which means that the probability that a student takes both of those things is 0.6. There's our answer. Now, as I mentioned before, I do also want to show this problem using the Venn diagram method where we're not sort of relying on the formula. So what this would look like is you would imagine a Venn diagram that has the H event and the B event. We know this one's 0.8 and this one over here is 0.7. And then we know this entire thing is supposed to be 0.9. So my thinking on this is, well, wait a minute, if I add 0.8 and 0.7 together, I'm going to get 1.5. But wait a minute, that means that these two circles are adding up to 1.5? That's too much. I overcounted by 0.6. That means this here has to be 0.6. And honestly, there's our answer right there. But you can also sort of work backward to see it. If this is 0.6, that means this region over here has to be 0.1, and this region has to be 0.2, because these have to add up to 0.7, this has to add up to 0.8, and we can really clearly see that all of these things add up to being 0.9. So I hope you guys are seeing that you can use either the Venn diagram or the formula. So in this problem, there isn't going to be any interpretation. You're just being given sort of like pure probability values and notation. And I want to remind you guys again, you can do this problem with either the formula or with a Venn diagram. I again will show both of them. Feel free to watch whichever part you need. One thing you may have noticed is that this question is asking for a complement. It's asking for not B, and none of our problems seems to have anything to do with not B. So remember that something we can do is we could maybe figure out what the probability of B is and then subtract it from 1 to go back and figure out what this is. So if I want to use my formula, I would really just be plugging the values into these. I have 0.6 here, I have 0.4 here. This is my unknown, so I'm going to leave it written as a notation, and my intersection was 0.25. So 0.6 equals 0.15, that's me just subtracting these things, plus the probability of B. So it looks like this is going to be 0.45 equals the probability of B. So using our formula, we were able to go pretty quickly to get that thing. Oops, and I just realized that I boxed that. It's not really fair for me to box that because that's not the answer. The question wanted the probability of not B, so I need to do 1 minus that, which means my answer is going to be 0.55. Okay, so this is the final answer to the problem. Now, for those of you that are interested in seeing how you would do this using just a Venn diagram, I'll go ahead and show that next. So we begin, unsurprisingly, by drawing a Venn diagram. All right, so here's my Venn diagram. This is my A event. This is my B event. Now, we were told in this problem that the probability of A was 0.4. So this whole circle is 0.4. We're told that the intersection was 0.25. So it's kind of interesting. As soon as I write that down, I kind of immediately want to say, well, wait a minute. If this whole circle is 0.4 and the intersection was 0.25, that automatically means that this is 0.15. Like I'm immediately sort of breaking this information down into digestible chunks. Then the next thing we were told that this entire thing was supposed to be 0.6. But again, wait a minute. If this is 0.4 and the whole thing is 0.6, that means that this over here is forced to be 0.2. Okay. Now I've got this stuff filled out, and there's actually another thing we can do. Wait a minute. If this is 0.6, the only region left in the diagram is like all of the outside stuff. All of the stuff that's outside of that symbol has to be 0.4. So with this one, I have a completely filled in Venn diagram, and so when the question asks, what's the probability of not B? I just look at it and say, well, wait a minute. If this is B, if that's B, then not B, the complement of B would just be all the stuff that's outside of B. When I put those two things together, I get 0.55. So the formula and the Venn diagram really are just different expressions of the same thing. The formula is expressing it with notation. The Venn diagram is expressing it with a diagram. So whichever of those sort of speaks more clearly to you, be ready for it. There are some problems that are really a lot easier to do with a diagram, or maybe only possible with a diagram, and I'm going to show you guys one of those in the next section. All right, I know this video is really, really, really long, and if you're still with me, you are a hero and you're doing great. This is a challenging problem, but if you've gotten this far, you can get through this one too. So here we go. Events A and B satisfy that relationship that's hard to even say out loud. It's the complement of the union of the complement of A and B. So if we know that's 0.3 and these two probabilities are both 0.5, find the probability of the union of A and the complement of B. So this is just like a giant alphabet soup, and you're looking at it going like, I don't even know what half of this stuff means. Like how do I even use a formula for this stuff? When they're really complicated like this, it can make sense to just go straight to the diagram and attempt to make sense of what it is that you're looking at. And it may take you a couple of Venn diagrams to try and really piece together what's happening here. So let's see what we can do. So I'm going to draw my Venn diagram here. This is A and this is B. Let's try and figure out what this information is saying. This first thing we need to think about this is the complement, so the opposite of not A or B. Now I don't want to mess up this nice diagram that I did, so let's make a little Venn diagram over here so I can investigate what's happening. So this thing is saying not A or B. So that would be not A Here's not A or B. So not A or any of B. So that's not A or B. All that stuff I just shaded in, that's not A or B. And they want the opposite of that. And I hope you can see there that the opposite of that is just this crescent. Well, it turns out that's actually really helpful for me. If that crescent is 0.3, it means that in my real diagram, I can label that as 0.3. Okay, now let's go on to my next piece of information. Right? My next piece of information tells me that, let's see here, tells me that the probability of not A is the same as the probability of B, which is 0.5. So not A, again, if you need to, go to another separate little Venn diagram. Not A means all the stuff that's outside of A. So all of this is 0.5. So in our diagram over here, it sort of means like that this and this together are 0.5. Okay? But again, wait a minute. If this is 0.3 and all of this stuff out here is 0.5, can't we tell what this is right here? Doesn't that mean that this region here has to be 0.2? Basically so that this can be 0.5 and all of the stuff outside of A can also be 0.5? Okay. Then as we continue on, we're told that the probability of B is 0.5, so the probability of B is also 0.5. So that means that this entire circle has to be 0.5. But, you can hear me saying it again, but if that circle's 0.5 and this part right here is already 0.2, it means that this part has to be 0.3. And then, I hope you guys notice, I don't even really care what the question is yet. I'm just filling out the diagram. My next step here is I can see 0.3 plus 0.2 plus 0.3, that's 0.8. This entire thing, all probabilities have to add up to 1. So since this entire thing has to add up to 1, I'm forced to say that the outside of this thing is 0.2. Okay? Now that I have my entire Venn diagram filled out, I'm going to go back and look at, hey, what is this thing? So I need one more little practice region over here. What would A union not B be? So A union not B would be A or not B, or anything outside of B. So that's all of this stuff. So A union not B, so I mean, based on what I have here then, that just means I need to add up this one, and this one, and this one. And that winds up being 0.7. And that's our answer for this one. So again, if you made it this far, you're awesome. I'm really sorry this video ran that long. In the beginning of the stuff in the intro, there's a lot of stuff that we need to cover, and I'm really trying to make this clear. So hope that made sense. If you've got questions, please make sure you ask them so I can help you out with it. Best of luck in the practice when we get to it.